Oh, it's 8 o'clock. Okay.
I'm a little slow this morning.
Okay.
Good morning, everybody.
Good morning.
My stupid phone. Good morning. My phone is ringing and it's nobody, so I will ignore it. Okay. You have a test coming up a week from tomorrow. Okay, exam 3, and it will cover the October 16th, October 23rd, and October 30th homeworks. And of course, you have homework due tomorrow too. Yeah, so the homework that's due tomorrow, that material will be on the exam, nothing after that.
Hello.
Hi. Question? Okay, so let's see.
Question.
Somebody have a question?
Yes. It's about the homework.
Okay.
On number 6, part D.
Okay, let me find it.
Is the second F equation supposed to be F prime?
No, it's not. And this one, if I remember correctly, does have a solution. Okay. The first 3 problems are what you call initial value problems. That part D is something called a boundary value problem. And in general, boundary value problems are a lot harder and don't always have solutions. But this one does. Okay.
Got it. Thank you.
You're welcome. Yeah, so you kind of have to leave the arbitrary constant in there until you'll have an arbitrary constant when you go from F double prime to F prime. Then you'll have another arbitrary constant when you go from F prime to F. You really can't solve for those constants, well, until you get back to F, and that means you're going to have a pair of linear equations in 2 unknowns. All right, so I'm going to go to my shared screen. Oops, there we go. Okay. And we're going to, we've been talking about area of regions for the past couple of days. We're going to generalize that a little bit. Okay. But this is, if your function f is above the x-axis, this definite integral is the same thing as the area under the curve. Okay. If f is a continuous function defined on the closed interval from a to b, so a is less than or equal to b. I think somebody needs to turn their microphone off.
Sorry, I just had one of my cats run over the button.
Okay. This happens. All right, so we divide the interval in AB into n subintervals. Okay, this is the partition of equal width. So the length of each subinterval is delta x equal to b minus a over n. All right, so you're dividing your big interval into n subintervals, and you enumerate the endpoints. You start with your left endpoint A, and that's x sub 0. And then you increment by 1 delta x, that gives you x1. And then you increment by another delta x, that gives you x2. And you keep incrementing until you reach the other endpoint B. Okay, so the endpoints of the subintervals x0, x1, x2, all the way up to xn. And then, okay, we talked about this a little bit yesterday. You pick sample points out of each one of those subintervals. And okay, the easiest thing to do is let the sample point be the right endpoint. So it's just x sub n itself. But that's not necessary. X sub I star can be any point in the interval x sub I minus 1 to x sub I. So having our partition x0 to x1, we pick out sample points from each of the sub intervals, call those x1 star, x2 star, all the way up to xn star. Oh, there's a lot of lead up here. Finally, the definite integral of f from a to b, okay, is this. Where's my pen? Where's my pen? Oh, here it is. Okay. So this funny notation, okay, but okay, the definition itself, this is what we were doing yesterday. It's a limit of Riemann sums. It's the limit as n goes to infinity of the sum as I goes from 1 to n of f of x by star delta x. And remember, if f is a positive function, if it's positive on the interval, this is just the area of a rectangle, each one of those. So in the case of a positive function, you're adding up areas of rectangles to get this big sum. And then you think of taking your intervals be smaller and smaller and smaller. You take the limit as n goes to infinity. And that limit you denote with this funny notation, okay? This was introduced by Leibniz. This funny symbol here, this curvy thing, it's kind of an elongated S. And well, that's sigma is an S too, basically. It's a Greek S. So they kind of go together. The dx is part of the whole definition, okay? And I think of the dx as telling me, well, the d something is in there. But the fact that it's x means that x is the variable for this integral. X actually represents any point between A and B. But okay, so just think of this as one blob. Okay, this is the way you denote this limit. And that is quite a definition. Okay, but it is as fundamental, if not more fundamental, than the idea of a derivative. Yes, and we're going to spend the rest of this semester and the first third of next semester talking about these things. These integrals. It's true that, well, it's more than a note, it's a theorem. If f is a continuous function on this closed interval, this limit exists, okay? If f is continuous and positive on the closed interval, the limit actually represents the area under the curve. But notice that there's no condition here in this definition that f has to be positive. So that's not part of the deal. It can be negative too. Still makes sense. Okay. Well, we don't have many tools for evaluating these things, but how about we use the fact that if f is positive, we're actually talking about area under the curve. So do with a couple of things if we can. Evaluate. Integral from 0 to 2 of 4 dx. Okay. And b, integral from 0 to 1. Oops. Forgot the integral sign. Of the square root of 1 minus x squared dx. Okay. What about part A? Well, what's the function here? It's a constant function. I'll call it 1, 2, 3, 4. Call that 4. Okay, and if this is 1, 2, then this integral, see, I don't really need, I have to erase the whole thing. Okay. This integral actually, so my function here is 4, constant function. And I go from 0 to 2. So the integral is actually going to give me the area of this rectangle. And I know that a rectangle has area length times width, so it's 2 times 4. The integral from 0 to 2 of 4 dx is 8. Okay. And again, I guess I'm hoping this corresponds to something I can compute the area of. Well, the square root of 1 minus x squared, that's actually part of a circle, right? The unit circle, in fact. You get y squared is 1 minus x squared. So y is plus or minus the square root of 1 minus x squared. And I've got plus, so actually I'm talking about the upper half of this unit circle. That's got way too much junk on it. Okay. And because it goes from 0 to 1 here, okay, I just start at 0 and stop at 1. So it's actually the part, I want the area of the part of the unit circle that's in the first quadrant. I want the area of this region. Well, I know that the area of a circle, in fact, we're going to be able to prove this actually later, but not until we do some more work. Area of a circle is pi r squared. This is the unit circle. So the area of the entire circle inside the entire unit circle is pi times 1 squared. But I don't want the entire region. I just want the part of the region that's in the first quadrant. So the area of the area inside, I should say. The circle itself doesn't have area. The area inside the circle. It's so the area here. Area inside the unit circle and in the first quadrant I should say area of the region would be 1/4 of pi. Okay, so that would be pi over 4. Now, well, we'd like to be able to do a lot more problems than this, but at this point we can at least do that. Yeah, and okay. From the definition is a definite integral, the definite integral from a to b of f of x dx is a limit of Riemann sums. These are all Riemann sums, all of these for each n. So if you want to approximate a definite integral, you can use Riemann sums to do it. Okay. And there are very sophisticated ways, okay, of using things, well, like the the trapezoid rule that Mr. Levy was thinking about doing, where you, instead of taking rectangles, you take trapezoids. That's a more sophisticated idea. Okay. Any questions before I go on?
Excuse me, Miss Kennedy, I do have a question. So what was the answer for the letter B problem?
Pi over 4.
Oh, my bad. Okay, powerful. Okay. Thank you. So just that.
That's okay. Yeah. Okay. All right. So properties. Okay, we have to get through some stuff. All right. And I know for most of you, this theoretical stuff, you probably just as soon skip it, but well, it is important. You have to have a foundation on which you can build, and we are laying that foundation. But let's see, it's going to take us a few days to get there. Okay. Here's property 1. The integral, the definite integral from A to B. So, okay. F is a continuous function defined on the closed interval AB. All right. So that's my definite integral. This is equal to minus the integral from B to A of f of x dx. So, okay, I reverse the endpoints. And, okay, let's go back to the definition. We had f of being a continuous function defined on the closed interval AB. Well, there's really nothing about this definition other than, you just kind of like to write your intervals, and so that A is the smallest number and B is the largest. There's nothing about the definition itself that says that A has to be less than B. When I go from B to A, what I'm essentially doing is turning delta X into a negative number. And when you do that, well, that's going to turn what would have been, okay, this Riemann sum, and it would be minus it if you go from B to A versus going from A to B. And that's going to put a minus sign in front of the integral, okay? So this is a property that always holds for definite integrals. Another property, the integral from A to A, so my interval consists of 1 point, is 0. And that makes sense. Okay, this is kind of like saying, okay, if I have a function, there's my function f, and I pick a number A. If I go from A to A, my interval consists of 1 point. My approximating rectangles would be vertical line segments. They have area 0. So since the area of a vertical line segment is 0, the definite integral is going to be 0. Okay. Yeah, also if it goes from A to A, then A is equal to B. That means delta X is going to be 0. Okay. So okay, number 3. The integral from A to B of a constant times a function. Well, you can pull the constant out. And the reason for that, okay, so constants can come out. Multiplied constants can come out. Nothing with an x can come out of the integral. But why should this be true? Well, go back to your definition. If I have, okay, it's a limit of Riemann sum. So let's just write that. Let's see. So this would be the limit as n approaches infinity of the sum as I goes from 1 to n of c times f of x of I star delta x, okay, because the function c times f, but this is a finite sum, each term of which has c as a factor. I can factor that c out of that sum and write it this way. And then I have, okay, this part has the n that's changing. This is just a constant. Well, I can put that c outside the limit too. Okay, it's one of the rules about limits, one of the limit laws. So basically, yeah, and this is the integral from a to b of c f of x dx, and this is c times the integral from a to b of f of x dx. Okay, so constants can come out. What if you're just integrating a constant? Can say even more. Oops. So it says integral from a to b of c dx. And again, if c is positive, this is going to be taking the area of a rectangle. Okay. So you have c here, and a could be actually. All right. Maybe a is here and b is here. And if c is positive, okay, so call that height c. Then this is just computing the area of a rectangle, which is going to be c times b minus a. But even if c is negative or 0, it still works. Say c is minus 1. So it's a constant function there. Well, now you've still got a rectangle involved, but it's completely beneath the x-axis. And actually that's going to make, instead of computing the area, you're going to get minus the area with the integral, okay? Because c's negative in here. But this rule still holds. C's negative, C's positive, or C's equal to 0. Okay, another rule, and again, these all come out of the definition. Definitions are so important if you're a mathematician. You have to know what it is you're talking about exactly. You know, say exactly what you mean, nothing more, nothing less. But if I have the sum of two functions, I can break it into the sum of the integrals. Okay.
Dr. Kennedy,
Yeah.
in the second box you got here, is that a 4 and an R there, or is that just gibberish?
4 and an R. Okay,
Or what do you,
where?
in the top of the second box?
Top of the second box. Oh, all right. Let's see. This box right here.
Yes, ma'am.
Okay. No, let's see.
In the top left and right sides.
Oh, I just called it A and B. Oh, I see where you're getting the R. right there.
Oh, is that just gibberish? All right.
Yeah. Yeah, it was
Gotcha.
just, yeah, that was a smear. Okay. Okay, and the reason this holds, again, it goes back to the definition, all right? It's a limit of those Riemann sums. Well, if you have a sum of numbers, you can break it into the sum of two sets of numbers. Oh, okay. Break it into the sum that I goes from 1 to n over 2, say, and then I goes from n over 2 to n, or however. No, that's not what you're doing. No, that's another rule. All right. But, well, okay. Let me just write it down. Okay. Instead of, yeah, this, we can prove this, actually. Because what's this first one? This would be the limit as n goes to infinity of the sum as I goes from 1 to n of f of x sub I star delta x. Oops. No, it's not. F of x sub I star plus g of x sub I star. Because that's my function for this interval, okay? But this is, okay, the sum of two numbers, and I can break it into, well, I can rearrange those numbers, right? Because addition under the real numbers, it commutes and associates. That is, f plus a plus b is b plus a, and a plus b plus c. Well, it's the same as if you take a plus b and then add c to it, or if you take a and then add b plus c to it. So because of the way the real numbers work, I can break this limit into two limits, and I'm going to do it in 2 steps. First of all, I can break my big Riemann sum into the sum of two Riemann sums. Okay, like that. And then from the limit laws, I can break that into the sum of two limits. My writing is a little bit, that's a delta, okay. And this is just the integral from a to b of x. And this is just the integral from a to b of g. So yeah, it actually, well, all these rules come straight out of the definition, okay? And the way that the real numbers behave, and then the limit laws. So that's another thing you can use. And then if you take rule number 5 and rule number 3 together, it's going to follow that. Okay, what was I up to? Rule 6. The integral from a to b of f of x minus g of x is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. Oh, I should say too, this notation, it kind of encapsulates the entire definition in this notation. Okay, so we're saying that the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I star delta x is equal to so the delta x here becomes the dx over there. And this sigma, that becomes that funny s. Okay. And then the a and the b are the endpoints of the interval you were dividing up into subintervals. And of course, then you've got your function inside. Actually, I think that's a kind of nice notation because it sort of keeps all the pieces. Anyway, so that was kind of an aside. Let's see. Okay. How about this? Well, we're going to get a number of more rules, but let's do a problem so we can use what we've just learned. Use the properties of integrals. Stop writing. Okay, just a minute. There, okay. I don't know why that works, but it does. Use the properties of integrals to evaluate the integral from 0 to 1 of 4 plus 3x dx. Okay, I think we can do this one. All right. Well, that's the sum of two functions. So I could use property 5 to break that into the sum of two integrals. So this is equal to the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x dx. This is property 5. And then, okay, well, 4 is a constant. 4 is just a plain constant, and we have this rule. Well, in fact, I'm going to be taking the area of a rectangle. Okay, so I can use the rule number 4. So this would be 4 times 1 minus 0. That's property 4. And then, okay, well, I can bring the 3 out because it's a constant. I can bring the 3 out of this one. And what rule was that? That was rule number 3. Okay, property 3. Okay, and then property 3, well, what's the integral from 0 to 1 of x? That's the area of that triangle, right? Because that's the function y equal to x. And the area of a triangle area of that triangle would be 1/2 the base times the height, which is 1/2. The base is length 1, the height is 1, so it's 1/2. And so I wind up with 4 plus 3. Well, this integral is 1/2. The integral from 0 to 1 of x dx would be 1/2. So 4 plus 3 halves, well, you can leave it written like that. But that's 8 halves plus 3 halves is 11 halves. I kind of like leaving it as an improper fraction. Or that's what they called it back in grade school. Yeah, I'm not much on rationalizing denominators either. Okay, any questions? Are y'all still there?
Yes, ma'am.
Okay, good. Okay, good. I have memories of that day my microphone went out. Okay. And also, I cut off all my notifications today because during my second class yesterday, I got a phone call. And when I get a phone call on my iPhone, it also comes to my iPad, and it kicked my class completely out. So live and learn. Okay, no notifications during class, which means I can't see if Mr. Miller sends me an email that says my microphone's off. I won't see it. Okay. All right. Anyway, that's beside the point. Okay. So we have how many so far? 5 rules so far?
6 rules.
6. Okay, 6. Yes, indeed. We have 6 so far. So here's number 7. And this one's really interesting, I think. If, okay, well, okay, f is continuous on a closed interval containing a, b, and c. So a little bit more than just the interval from a to b. Then the definite integral from a to b, a to c. It doesn't really matter, but okay, let me keep it that way. A to c is the integral from a to b plus the integral from b to c. Okay. Now, what does that say? Well, if f is positive, and maybe I should write f of x is, no, race. All right. If f of x is positive, and that's not necessary for this rule. I just want to illustrate here what this is saying, okay, in terms of areas. And there's my function. That's an x. So suppose we got a less than b less than c. Then the definite integral from a to c would be the area of this entire region, right? And the integral from a to b of f of x, well, that would just be the area of this piece of that region. But the integral from b to c of f, well, that would be the area of that piece. It makes sense that if I add this area plus that area, I would get the entire area. And that's what this property says. Okay, but you don't have to have A less than B less than C. Suppose that it still makes sense regardless. Okay, let's draw another picture. Suppose that I have A, C, B. So C's in the middle of that interval. It's inside of the interval AB. And then, okay, what am I talking about? The integral from A to C that would be the area of this region. That's the area of the yellow region. Okay, well, the integral from A to B I wonder if I can color over. Let's see. Let's see. Maybe I'll just pick a really pale green. How about that? Okay. The integral from A to B is the entire region, right? I can sort of color over it. This would be area of the green region, which is the entire region of the curve. And okay, well, what's the integral from B to C? Okay, in my picture now, the integral from B to C, okay, well, here I've got C less than B, so this is going through the integral backwards. Well, okay, use property 1. This would be minus the integral from C to B of f of x dx, which is minus the area of, okay, I guess I need another color. How about that one? Okay. Minus the area of that region right there. I'll call that orange. Of the orange region. So this rule, okay, let me remember how I wrote it. A to C. What does it say? It says that the integral of, okay, I've got too much junk on here now. Let me label this as region 1 and this as region 2. Okay. That the area of region 1 is equal to, okay, the area of region 1 union region 2. That's what A to B is. One union region 2 minus the area of region 2. And that makes sense, right? If you want the area of the entire region, well, if you got that area and you've got the entire area, you subtract the entire area minus the region 2 area to get the region 1 area. So this rule makes sense regardless of the order of the points A, B, and C. And it also makes sense whether or not f is a positive valued function. And it's a nice thing to know because sometimes it really helps if you can break your integral up like that. Okay. No time. About 9 minutes. Well, those are the most important ones so far, and in fact, I think what I'm going to say now follows from what we already have. Rule number 8. If f of x is positive for a less than or equal to x less than or equal to b, then the integral is not negative. Okay. And in fact, unless a is equal to b, that number is positive. Okay, let me just write that. Okay. Because we already know what happens if a is equal to b. This is positive as long as a is not equal to b. If you have a function that sits entirely above another function, then their integrals are going to follow the same pattern. And actually, this rule follows from this and from rule 6. Yeah. Okay. So it's what you call redundant. Okay, I'm going to write this in, but again, this is going to follow from everything else we've said. If m, so little m number, is less than or equal to f of x is less than or equal to big M for every x in the interval from a to b, then little m times b minus a is less than or equal to the integral from a to b of f of x. Dx is less than or equal to capital N times b minus a. Okay, this kind of makes sense if you think about it. Oh, so we have this function. There's f. Okay. And I take little m here and I take big M here. Okay, and call that A and call that B. Big M times B minus A. Well, in my picture, it'd be the area of that rectangle. Little m times B minus A. Well, little m's negative. So it's going to be the area, negative the area of that rectangle. And that says that the integral itself, well, basically it lies inside those two rectangles. Well, the part of the curve I'm interested in. Okay. And it's going to, oh, not quite. I didn't draw that right. Okay, let's see. My F should not be sticking out there. Okay. Because of this property right there. So there, that's better. Okay. It kind of makes sense that this would hold. In fact, if little m is positive, you're just looking at the area of a small rectangle and the area of a big rectangle, and your F is trapped in between, and it, yeah, it's a little bit harder to see. If that's little m and that's big M, and that's A and that's B, and F comes across like that, then big M times B minus A would be the area of that rectangle. Little m times B minus A would be the area of that rectangle, the red one there. The area under the curve is going to be somewhere between the area of the red rectangle and the area of the black rectangle, because the area or that would correspond to the area under the curve, which would be, okay, area of that region. Okay. And I think that finishes it. Let's see, I'm looking at my book here. That finishes our properties for the moment. And let's see, it's 8:52. This is a good stopping place. Okay, so all right. Got through all these 8 properties. They are really important. We will use them forever. Okay. But they're kind of natural when you think about it, and they are very useful to know about. Okay, so we'll pick up there tomorrow. And I might note I am already beyond what will be covered on the exam. So what's on the exam is only going to involve the material, well, up through the material you do for the homework this week. And okay, so class is over, and you can go if you need to. If you want to hang around and ask a question, please do.
Have a good day.